All right. So we have seen already example of group. So what a group is, and we know several examples. Uh, you can wonder if you can produce more examples, knowing the examples what we have so far. So can we produce more examples, uh, knowing the examples we have, right? So there are some ways to produce more examples. Let's just try to make a list of it, the ways we know. So for example, one of the way is that you can try to find various subgroups, right? If you can find in some way subgroup of the group, the examples you know, that will also give you example of groups, right? And number two, you can also find normal subgroups, but normal subgroup is just a subgroup, so it belongs to the family one in some sense. But once you have found a normal subgroup, you can construct quotients, which we saw last time, right? So you can construct quotients. So suppose I have a normal subgroup n, then you can construct G mod n, and that will give you some new examples, hopefully, right? Another way to construct more examples is as follows. So suppose I have phi, a group homomorphism from, let's say, group G1 to group G2. So suppose I have a group homomorphism between two groups, G1 and G2. Then what we do, we define what is called, so define first, define what is the kernel of this map phi. The kernel of this map phi is by definition a set of those elements in G1 uh, which under the map phi go to identity of G2. Yeah. So look at all those elements of G1 which go to identity element in G2. Certainly this contains identity. So this is always a non-empty subset. So this always contains identity. And we can also define image of this map, right? We also know what image of this map is. Simply we'll denote it by im phi, im phi. This is image of phi. So given a map, given a homomorphism, group homomorphism, we can have kernel of phi and image of phi. Then what happens is that kernel of phi, so this is the statement, kernel of phi is a normal subgroup, not just a subgroup, it's a normal subgroup of G1, because it of course is a subgroup of G1. Okay, we are not checked whether it's a subgroup, but it's a subset of G1. And in fact, it turns out, and image of phi is a subset of G2. It's a subgroup of G2. It may not be normal, but it's a subgroup of G2. Okay, let's verify these things. So this will also give you some examples of subgroups. I mean, you can produce more examples of group in some sense. If you know some group homomorphisms, then you can look at kernel and image. Okay, so let's verify. So verify these two. So first thing to verify, let's say this is 1 and this is 2. What can we say about kernel of phi? So kernel of phi is certainly a subset of G1. And we already checked that identity belongs to kernel of phi, because identity goes to identity under a group homomorphism. This we have checked, right? And we need to show that if I have two elements x, y in kernel of phi, then x into y also belongs to kernel of phi. How do we verify that?
Product of identity is identity. I mean, group multiplication of identities is identity.
I would use the definition of homomorphism. So I have to look at phi of xy, but the definition of homomorphism will say that I can write this as a phi x phi y, right? And I know x and y are already in kernels, so phi of x is identity and phi of y is also identity. So this is identity times identity, which is just identity, right? What is the question? Can there be a group homomorphism that is group of? No, I don't get the question, Shivang.
So I mean the phi's, the group of phi's, the homomorphism. Can there be a group of those also?
No, once again, I did not get it.
The group of homomorphism, the functions, the phi's.
Okay, so suppose I am given a group G1 and I'm given group G2. You want to
Uh,
collect set of all group homomorphism,
yeah,
and then you want to say that whether we can give some structure on that, right?
yes. So can it be a group or something?
So one obvious construction is, I mean, that's what that I would have mentioned after this, but let me just say here in this the set of constructions that if I am given a group G, you can take set of all automorphisms of G, which is called aut G. So aut G is all automorphisms of G, meaning the map from G which goes to itself, G to G, and it is an isomorphism, one onto map and group
Yeah.
homomorphism. The phi automorphism,
Hmm.
or other isomorphism, I should say here, I mean, because I'm just defining that. I think I defined automorphism, right?
Yes.
The phi is an isomorphism. So you collect all this, then
Okay.
this is a group under composition.
Okay.
Under composition. In general, if you are given G1, G2, I mean, of course, you can collect set of all maps, but how to define multiplication is not clear. Naturally, you would think of defining multiplication which uses something to do with the maps, right? So the natural thing to do on maps is compose them. But if you had G1 and G2 two different things, then you can't compose them generally, right? But this makes sense that if you have one group and you have all isomorphisms of that group on itself, then you can define composition. The composition is well defined, and then it becomes actually a group. And it's again an interesting exercise to calculate odd G for various examples of groups. I mean, this is like an open-ended exercise for you that all the examples of group you compute odd G for them. So exercise compute odd G for the examples. Certainly try one or two examples at least. Okay, so let's complete here what I was talking about. So first thing I want to check whether kernel of phi is a normal subgroup. So we can check that xy belonging to kernel of phi, then xy belongs to kernel of phi. And one more thing to check whether it's a group is if x belongs to kernel of phi, then x inverse also belongs to kernel of phi. Again, this comes from the property of homomorphism. So we know phi of x inverse is actually going to be phi of x whole inverse, right? Inverse will be outside. But we know that phi of x is identity. So this is identity inverse, and identity inverse is just identity. And now we need to check it's a normal subgroup, right? So to check it's a normal subgroup, you have to take G in G, and then you have to look at G kernel of phi G inverse. And we have to say that this is contained in kernel of phi. Okay. And I think you can verify that if I take any element here of the form G x G inverse and apply phi on that, so take phi of some G x G inverse, where x is coming from kernel of phi, then you will see that it is phi of G, phi of x will be identity, and phi of G inverse. And phi of G and phi of G inverse will cancel out to become identity. Okay, so that's why it's a normal subgroup. Verify this yourself. that this is a normal subgroup. And similarly, one can verify that uh, image of phi is a subgroup of G2. It need not be normal in general. But it's a subgroup. And again, you can verify all the properties. Clearly, identity belongs to image of phi because identity is equal to phi of E. So identity belongs to image of phi. If X and Y belongs to image of phi, then X into Y belongs to image of phi. How do I check this? So let's say X is some phi of G1 and Y is phi of G2. Then what we do is that we look at phi of G1 G2. This, by definition of group homomorphism, it is phi of G1 into phi of G2, and which is equal to X into Y. So you can see that XY also belongs to the image of phi. So this implies XY belongs to image of phi. And similarly, you can check inverse. So if X belongs to image of phi, then X inverse belongs to image of phi. And how do I do that? So I write X as, let's say, phi of some G. Then we try to compute phi of G inverse. Phi of G inverse will turn out to be phi of G whole inverse, which is X inverse. Right? So this verifies basically that image of phi is a subgroup. And this can be useful at times to find more examples of subgroups. We'll get back to this again, but let's write some more examples how to construct groups, and then we come back to this again. So the next example way of producing group is that suppose I know, so I am given a group G. G is a group, and suppose I have H, a subgroup of G. So suppose H is a subgroup. Then what we do? We define what is called normalizer of H. So define normalizer of H in G. That will be denoted by N H G below here. Okay, this is the notation for normalizer of H in G. And how do I define this? This is supposed to be all those elements of G such that if I compute X, H, X inverse, then it is contained in H or equal to H. Okay. Equality is also fine. Both are same. It will turn out that both are same, like we saw earlier. So this is normalizer of H in G. So you can notice that if H is a normal subgroup, then the normalizer is itself. You can't have something more. And normalizer of H always contains H. Some remarks or other properties. So property is this. H is contained in normalizer of H, which is of course contained in G. 2, normalizer of H in G is a subgroup, right? Is this clear? Normalizer of H in G is a subgroup. We need to verify that the properties of subgroup. So clearly identity belongs because of this first property that whole of H belongs. So identity belongs here. Check identity belongs to normalizer of H in G. And if X and Y are in normalizer, then XY is also in normalizer. This can be verified as follows. So I have to compute. So what is given to me? X, H, X inverse, is contained in H, and Y H Y inverse is also contained in H. That is given to me, and then I have to compute X Y H X Y inverse. Okay, and this is going to be X Y H X Y inverse is Y inverse X inverse, right? So let's first look at this part here. By this one here, we see that this is a subset of X H X inverse, right? This may not be, I mean, my definition says there is subset, but actually it will turn out to be equal, then matters. And then this whole thing, by looking at this one here, we know that this will be contained in H. So this is what verifies that. And same thing we can do for the third property, that if X is a normalizer, then X inverse is also a normalizer. Okay. Did I say the property? Yeah. So normalizer is a subgroup. H is a subset of these. Third property which I wanted to say, that what happens if H is normal, right? So the third property here I wanted to say, if H is normal, then it turns out that normalizer of H in G is equal to G, right? Do you remember the definition of normal subgroup? That any G in G, G H G inverse is contained in H for any G. So that is why it will turn out to be equal. Okay, so there is one of the definition, and the another definition I'm going to make is what is called centralizer. Centralizer of H in G. This is denoted as CHG. This is going to be those elements of G such that X fixes every point of H one by one. X inverse is H for all H in H. Notice the difference between the two definitions. So this also implies that XH is actually HX, right? I mean, I can move the X inverse on the other side by multiplying with X. So this equation is same as this equation. XH is HX. And this will happen for all H in H. So what's the difference between the two definitions? The normalizer definition and centralizer definition?
In the normalizer, your elements can be permuted inside the group. Here, they need to be fixed.
Right. So you have to keep this in mind. Often people think that, oh, the two definitions are same. I mean, there is not much difference. What making it a billion? Yeah, I mean, all those elements which commute with every element of H, point-wise in some sense, right? And unlike in the normalizer, where actually it can permute. I mean, X inverse doesn't need to be H. It could be some other H dash or something. That is normalizer definition. It's always good to again compute some examples and practice this. Okay. So again, properties, you can write down the properties of this. Of course, the first property is this, that so is it true that H is contained in centralizer of H in G?
Only if H is abelian, something like that.
Yes. So in general, that may not be even true. But centralizer of H
Is
in
contained
G,
in H, no?
sorry?
Is centralizer? Okay, wait, never mind. Okay, nothing.
Yeah, that's a question I asked, that whether H is contained in centralizer of H in G in general. So this is certainly contained in normalizer of H in G, right? But the question I asked, so Is it true? H is contained in centralizer of H in G.
Not necessarily, because if H is not abelian, then it won't be.
It may not happen, yes, true. But we have to give some example. So what Amog says, centralizer of H will also be a normalizer, right? Yeah, so that's what I said. Centralizer is contained in normalizer. Of course, normalizer is much bigger. Certainly, it contains H and it could have much more elements. But it might be even so that centralizer does not contain H. So, do you have any example? Can you think of any example?
The dihedral group. So RS, RNOS won't be S.
Right. Okay.
Dihedral group of order 3, let's say.
Okay. So
Order
let's write
6, I
down this
mean.
example. Yeah. Let's write down the example. Let's work with S3. S3 is same as the D6.
Yeah.
They're isomorphic. So S3 has 6 elements, and we'll see if we can find an example here. So 1, 2, 1, 3, 2, 3, 1, 2, 3, and 1, 3, 2. These are 6 elements. And okay.
Yeah,
Okay,
1, 2, 3.
here
1,
it
2,
will turn
1.
out probably that centralizer contains H. In this case, you probably will not see that example, but certainly normalizer is bigger here. That example you can probably see. So, for example, if I take H to be 1, 1, 2, 3, and 1, 3, 2, then normalizer of H in S3 is what? So it will certainly contain H. Now the question is that whether it contains anything from outside. Can anyone compute and tell me?
Is
I
it
think
equal to H?
It will turn out to be whole of S3 probably.
it will be all of us.
So let's check one at least practice one thing. I mean, let's work out one example at least here. 1, 2, 3, and 1, 2. So we have to conjugate H by 1, 2, right? And see whether it is contained in that only. This is what I want to compute. So I'll just computing one example inside this. What will happen to this? So this is going to be 1, 2, 1, 2, 3, and 1, 2. 1, 2 inverse is just 1, 2. What is this final element? 1 goes to 3, 3 goes to 3, 3 goes to 1, 1 goes to 2. You get this element. And so this is kind of permuting 1, 2, 3 to 1, 3, 2, and 1, 3, 2 will go to 1, 2, 3 by if you compute here for that element, right? So that means this is correct. What is centralizer of H? Centralizer of H in S3? So notice that H is abelian here, right? So whenever H is abelian, it will contain H itself. And the computation here, what I did just now shows that nothing else. It will turn out to be equal to H, in fact, here, right? Is that clear? So we don't have example of the situation that H is not contained in centralizer yet. Can you tell
What
me
if
some
we
other
take
example?
the entire? What if we take S3, the entire group as H?
Okay. That's a good thing. So
Then normalizer will be entire group,
yeah,
and
if I take H to be S3 itself, then compute centralizer of H in S3, then what do you get? It will turn out to be identity. So this is definition here again. I'll make this definition. What is called center of a group. Center of a group G. So center of a group is sometimes it is denoted as Z of G. Z of G. This is by definition all those elements of G which commute with every element of G. In another way, it is supposed to be centralizer of the group G in itself, right? The two things are same. So that's what that's how I get that example here.
Sir, H always contains centralizer, no?
Sorry, H always contains.
Centralizer, or is that not true always? Like your question was, does centralizer contain H? I'm asking if H contains centralizer.
H.
no, it won't, right? Because
Why?
yeah, it won't.
Why?
Okay.
Yeah. So here is, let's do some other example maybe. Uh, have you practiced working with S4? So here is an example. S4. So in S4, I have element, let's say 1, 2, right? So I can make the subgroup H equal to 1 and 1, 2 because it's an order 2 element, so this will become a subgroup, right? Now, what is supposed to be centralizer of H in S4? My claim is that 3, 4 belongs to the centralizer.
Yeah, because the cycles are distant.
Yeah, okay.
So 1,
I see
2,
it.
3, 4 is equal to 3, 4 times 1, 2.
Thank you. So both need not be true, right? Like both the
Yes,
questions. H
yes,
belongs to centralizer and centralizer belong to H.
yes. So they are quite different kind of objects. So it's a good thing. It will construct you some subgroups. So centralizer is supposed to be a subgroup, and it gives you, it can allow you to construct more examples of subgroups, right? Okay. So I defined, okay, I defined normalizer, centralizer of subgroup. Now question is that can we have normalizer and centralizer of one element, right? So what we do normally, you can directly take it as a definition, or you can think of defining it using the earlier definition. So if I have some element X in G, then we define centralizer of X in G, which is this to be centralizer of subgroup generated by X in G. So instead of writing this complicated way, you can think of simply this as all those elements of G which commute with X, right? It's clear? For a single element, if I have a single element, I can define its centralizer, and this will contain X always, right? X, because X commutes with itself. So X always belongs to centralizer of X in G. It's also a subgroup, so identity always belongs here. It's always a subgroup. So this is a subgroup of G. And well, normalizer doesn't make much sense here. Normalizer will turn out to be the centralizer itself for a single element. So we don't define normalizer for a single element. Okay, so these are some ways to produce more examples. One more way to produce examples is what is called taking direct product. So suppose I am given two groups, G1 and G2 are groups. What I do is that I take the set G1 cross G2. Okay, Cartesian product. So G1 cross G2 is by definition elements coming from G1 and elements coming from G2. And G2 is in G2. Okay, so I just said this is supposed to be just the Cartesian product. What is the multiplication here? So I have to multiply two such elements. I have suppose element G1 comma G2, and I have another element, let's say H1 comma H2, and I define multiplication. How do I define the multiplication here? So suppose these are the element in G1 cross G2. I will define the multiplication G1 comma G2 into H1 comma H2 using the multiplication of G1 and multiplication of G2, right? So I'll simply do that. I take G1 H1 in the first component and G2 H2 in the second component. This is how I define this multiplication here. The definition of this multiplication. Then G1 cross G2 is a group. In fact, you can keep multiplying. If you have more groups, you can keep multiplying and you will get, I mean, certainly you can keep multiplying finitely many times and you can keep getting more and more examples, right? For example, yes.
No, I have a doubt about something else.
Yes.
Yeah. So in the when we define normalizer and centralizer for a single for a single element, you said that the normalizer will end up being the centralizer.
Yes.
But that won't be true. So I think if you take S3 with the subgroup 1 and 1, 2, then your centralizer would just be that and that subgroup, right?
Centralizer of 1, 2.
Yeah.
Yeah.
Will just be 1 and 1, 2.
Right.
But your normalizer would contain the 3 cycles also because.
Okay. Yeah, so normalizer, yeah, you can have that definition of normalizer, but it's not often used. But anyway, it's not that important right now.
Okay.
But that is how you would define if you want to define normalizer of an element.
So in a similar fashion, just take that subgroup and then define.
Yeah, exactly.
Okay.
So it doesn't give something interesting. Centralizer is quite used often, so I define centralizer separately.
Yeah, okay, I was just confused.
Okay.
Yeah.
Right. Okay. So so you can take, for example, Z mod 2Z cross Z mod 2Z, right? And you will see that this is not Z mod 4Z. You have to prove this, that these two groups are not isomorphic. They're not same. Why? Can anyone say that? Tell me why this is not true.
Because Z mod 2Z cross Z mod 2Z has no elements of order 4.
Yes. So if you check the order of the elements here, all the elements will be of order 2 here. So all elements have order 2. But this has an element of order 4. This is because if you have a homomorphism, the order isomorphism, then the order is preserved in an isomorphism. Okay, so these are some examples these are some ways to produce more examples. So let's discuss a little bit more about this homomorphisms. So what is the role of?
Sir, do we need the GCD of the two of them to be equal to 1 for having it as isomorphic to Z mod, say M and Z?
If you are looking at only cyclic group, yes, that will be that will be a good situation. That is when it will happen.
Okay.
You are right. That
Otherwise,
is, I mean, we can take direct product of non-commutative groups also, right? And then there, like, no such thing will happen. We don't know that.
yes, yes.
Even if one of the group is non-commutative, the product will remain non-commutative, right? Because after all, you are multiplying the component only.
Yes.
So, but if you are a cyclic group like this, and if you are trying to take the direct product, then DCD will play that role when it becomes cyclic again. Okay, so what is the role of kernel of phi and image of phi? So here it is. So why? So first claim is kernel of phi. We know kernel of phi is a normal subgroup, right? So remember, phi is a map group homomorphism from G1 to G2. So kernel of phi is a normal subgroup of G1. So kernel of phi is identity if and only if phi is injective. Okay. And the second thing is kind of obvious, that image of phi is whole of G2 if and only if phi is surjective. Right. So the first one is very useful. Instead of proving injectivity of a map, sometimes it's easier to check kernel of phi is trivial. Kernel of phi does not contain any non-trivial element. Right. So let's verify the first one, and then we can try to write one or two examples of homomorphisms and see if we can get something. Okay. So proof of one, basically, right? I mean, two is automatic, so proof of one. So suppose I'm given, so let's say we are trying to prove this way. So we are given kernel of phi is identity. We need to show that phi is injective. To show phi is injective. What do you mean? How do I show phi is injective? If phi of some x1 is equal to phi of x2, then this would imply x1 is equal to x2 for all x1, x2 in G1. Is that correct?
Yes, sir.
Yes, what Abhinav says that this is somewhat similar to what you have done in linear algebra, something like rank nullity theorem. It's an analog to that in a way. There also you have definition of kernel and image. That's what it is here. So, okay, so to show phi of x1 is phi of x2 implies x1 is equal to x2. So let's do that. If I have phi of x1 equal to phi of x2, I can multiply by the inverse of phi x2, right? So phi x1, phi of x2 inverse is identity. And we know that when I take inverse of a element, then I can take the inverse inside. Now I'll use the definition of homomorphism. So this becomes this, right? So this will imply that x1, x2 inverse belongs to kernel of phi, which is given to be just identity. It has a single element. So that means x1, x2 inverse is identity. This is given to be just single element identity. And that's why x1 is equal to x2. Correct? We can prove the other way around also. If you want to prove this way. So what is this way? That we are given injective map and show that kernel is trivial. So phi injective implies kernel of phi is trivial. This is the question. So okay, so suppose there is some non-trivial element in kernel of phi. Suppose x belongs to kernel of phi and x is not equal to identity. But then if I look at phi of x, and phi of x is supposed to be identity, right? And that contradicts injectivity. Injectivity will imply that, so injectivity will imply x is identity, and that is a contradiction. Okay, that was quite easy to prove, but it allows you to verify something is injective or not, and sometimes it's easier to verify this property. Okay, I'll just maybe write down one or two examples, and then we can stop. So some examples of homomorphism. So we are seeing matrix group, right? So let's say GLN R. So I define a map from GLN R to R star. So when I say R star, then I'm thinking of real numbers with multiplication, right? Non-zero real number with multiplication. I define this map, so phi. I define this map that phi of any matrix A is determinant of A. So my claim is that this is a group homomorphism. Why is that?
Because of
Because
the determinant of a product of matrices is like the product of
Product of
determinants.
determinant. Right. So that is what you use here to show that this is a group homomorphism. And what is kernel of phi?
SLN R.
Yeah, all elements which go to 1, right? And that is the SLN R. All those matrices of which determinant is 1. So by general definition, kernel of phi is a normal subgroup. So this will say that SLN R is a normal subgroup of GLN R, right? What would be image here? What is the image of determinant map?
it is surjective, like
Why?
the full of R star.
Yeah.
Why?
Because you can multiply any row of GLNR of A, and with a real number. You take SLNR, a matrix SLNR, and then multiply one of its rows with any real number. Now its determinant will be equal to that real number. So we have.
So basically, you need to give me explicit matrix of which determinant is a particular real number. How do you do that?
Yeah,
Yeah.
so what Ravi said only, we can take first row and first column to be that real number, and then we can take all the diagonal entries to be one. I mean, the simplest example of it.
Yes.
Right? This will work. Okay. Some more example. If I look at the real number with addition, and I want to define a map to complex number with multiplication. And this is just the exponential map. So if I take any t going to e to power 2 pi I t, right? What is the kernel of this map? First of all, it's a group homomorphism. Is that clear? It's a group homomorphism. Because e to power 2 pi I t1 plus t2 is e to power 2 pi I t1 into e to power 2 pi I t2. So it's a group homomorphism. What is kernel of this map? So let's say this map is 5. What is kernel of
0.
5? Y is 0.
2n pi, right? Where n is a natural number.
I think it will be integers.
Yeah.
Integer.
Yeah, integers, sorry, not 2n pi.
So kernel of this map is integers. Because if you take 2 pi I t plus some integer, then it just remains 2 pi I t, right? 2 pi I to the power, no, sorry. E to power 2 pi I, some integer is basically 1, right? What is the image of phi?
The circle, unit circle.
Yeah,
So
it's
this
a
is
unit
circle.
circle in complex.
It's also called S1. So this is circle. Okay. Just one or two more example maybe. I mean, one easy example. So suppose I have a Abelian group Z. I want to define map from Z to Z. So take any integer, define it by multiplication by that m, where m is an integer, right? It's a group homomorphism. Fixed m. It's a group homomorphism. What is kernel of this map? And what is image of this map?
Kernel will be 0 if m is not 0.
Yes, so it is 0 if m is not 0. And if m is 0, then kernel is everything.
Yes.
What about image? Suppose m is not 0. Let's say m is not 0 here.
It is a
M-
coset, right?
It would be
Sorry?
MZ
Yeah, MZ.
It
left
will be
pocket.
mz, all multiples of m. Right? Yeah. Yeah. So these are some examples. We'll continue next time with some more properties and a theorem maybe. Okay. So if you have any question, we can discuss that.
So one doubt I had while constructing the normalizer, what we do basically is we take for the subgroup H,